Have you ever just stopped and noticed the rhythm of the world? I mean, really noticed it? From the tiniest atoms to the biggest things we build, our entire universe is just full of stuff moving back and forth over and over again. This is the world of oscillations. And honestly, it's one of the most fundamental ideas in all of physics and engineering. So, let's get into it.
Just think about a really strong wind hitting a power line. It's not just a steady push, right? The line can start to swing and bounce like crazy. Engineers actually call this galloping, and it can get so violent that it literally tears the line apart.
Or how about this one? A train going around a curve. Its wheels don't just smoothly turn, they actually oscillate side to side on the track. It's a motion called hunting, and it's what you hear as that rhythmic clatter when a train goes by.
And maybe the wildest example, when an archer fires an arrow, it doesn't fly perfectly straight at first. No way! It actually flexes and wobbles, oscillating as it leaves the bow. And that's not a flaw. That oscillation is exactly what lets the feathers snake around the bow instead of smacking right into it. These aren't just random movements. They are all oscillations.
So what's the common thread here? Well, they're all oscillations, and all that means is it's any motion that repeats itself at regular intervals. You might also hear it called periodic or harmonic motion, but no matter the name, understanding this concept is absolutely key to understanding the world. All right, so here's our game plan. We're going to start with the basics, the rhythm of the universe. Then, we'll dissect the anatomy of a perfect wave. After that, we'll look at the force behind the motion. Check out pendulums, gravity's rhythm, and finally, see how this all works in oscillations in the real world. Okay, so to get a handle on this rhythm of the universe, we first need a way to talk about it, to describe it. And, just like with music, the most important thing about any oscillation is its tempo. How fast is it beating?
So we've got two main ways to measure this rhythm, and they're really just two sides of the same coin. First, there's frequency, which we write as F. This just counts how many full back and forth cycles happen every single second. The unit for that is hertz, so if something is oscillating at 10 hertz, it's doing 10 full cycles a second. Now the flip side is the period, written as T. That's just the time it takes to complete one of those cycles. They're perfect inverses of each other. If you know one, you always know the other.
Now, tons of things oscillate, but physicists, well, they love to start with the simplest, most perfect case imaginable. We call this simple harmonic motion, or SHM for short. And here's the absolute key. In SHM, the force that pulls the object back to the middle, we call that the restoring force, is always directly proportional to how far away you've moved it. It's simple. Pull it twice as far, the force pulling back is twice as strong. That simple relationship is what creates the purest, most perfect oscillation you can get.
So, how do we actually describe this perfect motion with math? Well, believe it or not, it all comes down to one single, really elegant equation. I know it might look a little intimidating at first glance, but let's break it down. Just think of it like the recipe for a perfect wave.
And here it is. This is the master equation. All it does is tell you the position, x, of the object at any given time, t. Everything else you see, the xm, the omega, and the phi, those are just constants. Think of them as the control dials you can turn to change how the wave looks and behaves.
Let's look at those dials. The amplitude, xm, is the easiest one. That's just how far the object gets from the center point. It's the size or the height of the wave. Then we have the angular frequency, omega. That's omega. It's basically the speed of the wave, telling you how quickly the oscillations happen. A bigger omega means a faster oscillation. And last, we have the phase, phi, or phi-y. This is just the starting point. It tells us where the object was right at the beginning, at time 0, which has the effect of shifting the whole wave left or right.
So what does this motion actually look like when you plot it out? This graph shows us exactly that. This is the object's position, or displacement, over time. And you can see it move so smoothly back and forth between its maximum positive and negative amplitude, xm, tracing out this perfect, beautiful cosine wave.
Okay, but here's where it gets really interesting. Let's look at the velocity. This second graph shows that the object's speed is totally out of sync with its position. I mean, think about it. When the object is at its furthest point away, at maximum displacement, it has to stop for a split second to turn around. So its velocity is 0. But when it's zipping through the center point where displacement is 0, that's when it's moving its absolute fastest.
And finally, we have the acceleration in this third graph. Just look at it. It's a perfect mirror image of the displacement graph. When the object is at its maximum positive position, way out to the right, that restoring force is yanking it back as hard as it can. That means it has a maximum negative acceleration. The acceleration is always pointing in the opposite direction of the displacement.
And that relationship brings us to the true signature, the absolute hallmark of simple harmonic motion. This little equation right here. It says that the acceleration is directly proportional to the displacement, but in the opposite direction. If you ever see this relationship in any system, you know without a doubt that you are looking at simple harmonic motion. It's the defining characteristic.
So we've done a great job describing the motion. But what's actually causing it? What's the physical force behind this perfect back-and-forth dance?
Well, the classic example, the one you see in every textbook, is a spring. Hooke's law tells us that the force from a spring is equal to its displacement x times a spring constant k, which is just a measure of its stiffness. But that minus sign, that's the crucial part. It tells us the force is always a restoring force, always pulling back towards the center. This is literally the engine that drives simple harmonic motion.
Now, let's follow the energy. In a perfect world with no friction, the total energy in the system never changes. It just transforms from one type to another. So at the furthest points, when the block has stopped for an instant, all the energy is potential energy, stored up in that stretched or compressed spring. Then, as the block comes rushing back through the center, all that potential energy gets converted into kinetic energy, the energy of motion. It's this continuous, beautiful trade-off that just keeps the whole cycle going.
Okay, springs are great, but let's be honest, there is an even more common oscillator that you've probably seen 1,000 times, the pendulum. But here, it isn't a spring that's providing the restoring force. Nope, it's gravity itself. Now, physicists love to start with a simple pendulum, this idealized model where all the mass is just a single point at the end of a weightless string. But the same principles work for a physical pendulum, which is just any real object that's swinging, like your leg or a grandfather clock's arm. And the key insight, for small swings at least, is that the bit of gravity that pulls the bob back to the center is directly proportional to its displacement. Now, does that sound familiar? It should. It's the exact same condition as Hooke's law, and that's why pendulums perform such beautiful, simple harmonic motion.
So far, we've been living in this perfect, frictionless world. But in reality, well, things get a little messy. And there are two really important factors that change how oscillations behave in the real world: damping and resonance.
So why does a pendulum eventually stop swinging, or a guitar string stop humming? The answer is damping. You've got forces like air resistance or friction where it pivots, and these forces work against the motion. They slowly drain the energy out of the system, and you can see it right here in this graph. The amplitude just gets smaller and smaller and smaller with each swing until the motion just dies out.
But what if, instead of taking energy away, you add it? Think about pushing someone on a swing. You can't just push whenever you want, right? You have to push at just the right moment, in sync with the swing's natural rhythm. That phenomenon is called resonance. When the frequency of your push perfectly matches the system's natural frequency, the amplitude can grow and grow, sometimes to incredible levels.
And resonance isn't just for playground swings. It can have absolutely catastrophic consequences. Back in 1985, a massive earthquake hit off the coast of Mexico. By the time the seismic waves actually reached Mexico City, they were pretty weak. But, and this is a huge but, the city is built on soft soil that started to shake at a very specific frequency. And tragically, that frequency happened to match the natural resonant frequency of many of the city's mid-sized buildings. It caused them to oscillate so violently that they just shook themselves apart.
When you step back and look at it, oscillations are truly everywhere, from a tiny squeak in your car to the massive forces that can level a city. And the principles we've talked about, simple harmonic motion, damping, and resonance, those are the keys to understanding this universal rhythm. So that leaves us with a final thought. If a tiny periodic push can amplify motion enough to topple buildings, where else in your world might you see the hidden power of resonance at work?